Welcome to my 48th tutoring session in A-level chemistry. In this video, I'll explain the chemical properties of halogens. Take a moment to watch my previous video on the topic physical properties of halogens, as the video will provide you with a better understanding of this video content. Link to the video is given in the description below. Please do watch the video. Kindly subscribe my channel, share, like, comment, and watch the full video. Now, halogens belong to the 7th group in the periodic table. And there are a total of 7 valence electrons in the outermost shell of halogens. Now, here's the electronic structure of the halogens. Fluorine having 2 shells, chlorine having 3 shells, bromine has 4 shells, and iodine has a total of 5 shells, with 7 valence electrons in the outermost shell. Now, halogens do not exist in the elemental form. They exist in the molecular form. That is, halogens exist as diatomic molecules by sharing electrons between the atoms involved in bond formation. For example, chlorine molecule is formed by mutual sharing of electron pair between 2 chlorine atoms, resulting in formation of molecular chlorine. Now, acetone also belongs to the 7th group, but it is radioactive in nature and it is prepared by nuclear reaction. So, we'll kind of ignore this radioactive element that belongs to the 7th group. Now, the oxidation state of halogens in the neutral form is 0. And halogens, they tend to form covalent bonds with non-metals like hydrogen and carbon. For example, fluorine reacts with hydrogen to form hydrogen fluoride. Chlorine reacts with hydrogen to form hydrogen chloride. Bromine reacts with hydrogen to form hydrogen bromide. And iodine reacts with hydrogen to form hydrogen iodide. The other examples include halogenated hydrocarbons like methyl chloride, dichloromethane, chloroform, and carbon tetrachloride. So all these halogenated compounds, they involve covalent bond in their molecule. The covalent bond is formed between hydrogen and fluorine by mutual sharing of electrons, and that leads to formation of covalent bond. Now, halogens, they form covalent bonds with non-metals, while they form ionic bonds with metals. Now, here M stands for metal and X stands for halogen. Now, ionic bonds are formed by transfer of electrons, by the complete transfer of electrons from metal to the halogen atom. And after the halogen atom has received the electron from the metal, its oxidation state changes from 0 to -1, because the halogen, after accepting an electron from the metal atom, it is rich by 1 electron, and thereby the oxidation state changes from 0 to -1. Now, as you go down the 7th group, where you find the halogens, the periodic table, the shells increase. But though the number of shells increase as you go down the group, it is the 7th group, the number of valence electrons remain one and the same. So each halogen atom has a total of 7 valence electrons in the outermost shell. And as you go down the group, there is shielding. The shielding increases, atomic radius increases, ionization energy decreases. There is an increase in shielding that wins over an increasing nuclear charge. Additionally, electronegativity decreases and the melting and boiling point of the halogens increase going down the group. I'll kind of skip these points as these points have been dealt in detail in my previous video. So further details on this highlighted points, you can refer my previous video. Now talking about reactivity of halogens. Now reactivity is all about accepting electron or donating electron in a given reaction. Now halogens generally they have a tendency to accept an electron in a reaction. For example, now fluorine, it accepts an electron in a reaction and thereby it acts as an oxidizing agent. So halogens generally they accept an electron in a reaction, it is a redox reaction, and acts as an oxidizing agent. Now going down the group, this particular tendency of the halogen atom to accept an electron, it decreases. It decreases because of the 6 highlighting points that I mentioned now. So all these factors together, they contribute towards the reduction in the oxidizing power going down the group. Now when an halogen reacts, each atom, it gains an electron to give an halide ion. And that is how the halogens act as oxidizing agents. Now in the neutral molecular form, oxidation state of halogen is 0, while the oxidation state is -1 in the halide form. So after the halogen accepts an electron, it becomes rich by 1 electron and there is a change in oxidation state from 0 to -1. Because after accepting electron, the outermost valence electron is rich by 1 more electron. Now what makes the halogen atom to accept an electron? There are 2 reasons for this. The first being, it wants to complete the outermost shell, it wants to complete the octet, and it wants to attain the stable electronic configuration of the nearest noble gas in the periodic table. So these are the 2 major reasons for the halogen atom to accept an electron. Now halogens also exhibit displacement reactions. Now in a displacement reaction, the ions in the solution, it turns into an element. And this displacement reaction can be visualized either by color change or by appearance of a precipitate. For example, when you treat bromide ion solution with chlorine, chlorine oxidizes the bromide ion and liberates bromine during the reaction, and in the course of reaction the chlorine molecule gets reduced and it turns into a halide ion. Why chlorine oxidizes bromine? So when you treat the solution of bromide ion with chlorine gas, it takes an electron from the bromide ion because chlorine is more, or it is a strong oxidizing agent as compared to bromine. So that is the primary reason for chlorine to oxidize bromine. So it not only accepts or oxidizes bromine, it also oxidizes iodine as well. So chlorine is a powerful oxidizing agent. Its oxidizing power is greater as compared to bromine and iodine. And that is the reason behind chlorine having an ability to oxidize both bromine and iodine in redox reaction. Now fluorine and chlorine are gaseous in nature, while bromine is a reddish brown liquid and iodine is a black solid. But when iodine is in the vapor form, when it tries to escape in the vapor form, you see the purple vapors. Now going down the seventh group, you see the number of shells increase. Now fluorine has 2 shells, chlorine has 3 shells, bromine has 4 shells, while iodine has 5 shells. So as you go down the group, there is increase in the number of shells. Now the outermost shell for the halogens, they have a total of 7 valence electrons. And they need just one more electron to complete the octet. And that is why they act as oxidizing agents. That is, they have the tendency to accept an electron in a reaction. Now going down the group, atomic radius increases, shielding increases. An increase in shielding wins over an increase in nuclear charge. And the attraction between the nuclear protons and the outermost electrons also decreases. So I'll be skipping the explanation about these 6 points as they have been dealt in detail in my previous video. Now as we go down the 7th group, the electronegativity decreases, and the reason for the decrease in electronegativity will be explained in detail later in the video. And the reactivity also decreases going down the group. So reactivity of halogens generally is referred in terms of its oxidizing power. So oxidizing power decreases going down the group. So by taking up an extra electron, the halogens complete the octet, and this is because they have a tendency to adopt the noble gas electron structures. So if an element takes one or more electrons during a reaction, then it is acting as an oxidizing agent. So the transformation of halogen molecule with an oxidation state of 0 to halide ion with an oxidation state of -1 is represented with the redox reaction between chlorine and bromide ion. So during the reaction between chlorine and bromide ion, chlorine is getting reduced while the bromine is getting oxidized. So generally when an halogen reacts, so each atom in the halogen gains an electron to give a halide ion. So oxidation state of chlorine atom is 0 in molecular chlorine, while the oxidation state of the chlorine atom in the halide ion is -1, as it is rich by 1 electron after the redox reaction. Now a little bit more about the displacement reactions. Now halogens, they exhibit displacement reactions. And let us try and understand the mechanism involved in displacement reactions with the help of electronic structures of fluorine, chlorine, bromine and iodine. Now generally in a displacement reaction, the ions in the solution, they are turned into element, and this can be visualized in terms of color change or by the formation of a precipitate. So for example, chlorine will displace bromine and iodine because it is a better oxidizing agent. So this reaction has already been dealt with. So during displacement reaction, the halogen tends to gain an electron So fluorine, it gains an electron. It completes the octet. Similarly, chlorine, it gains an electron. Bromine gains an electron. And iodine also gains an electron. So by gaining electron, the fluorine attains the electronic configuration of noble gas neon. Chlorine attains the stable electronic configuration of argon. Bromine attains the electronic configuration of krypton, while iodine, it attains the stable electronic configuration of xenon. So by taking up an electron, halogens acts as an oxidizing agent. Now, what is the driving force for the displacement reactions of halogens? The major reasons being to attain the stable electronic configuration of the nearest noble gas. For example, fluorine. So all the halogens, they have a total of 7 valence electrons in the outermost shell, and they need just 1 electron to complete the octet. So in order to complete the octet, they take an electron during a reaction, and thereby they attain the stable electronic configuration of the nearest noble gas. So in case of fluorine, the nearest noble gas is neon. In case of chlorine, the nearest noble gas is argon. In case of bromine, the nearest noble gas is krypton. And in case of iodine, the nearest noble gas in the periodic table is xenon. Now talking about the bond energy of halogens. Now bond energy is the amount of energy required to break a bond. Now the other synonymous names used to express bond energy is bond enthalpy and bond strength. Now bond energy or bond strength or bond enthalpy is generally expressed in kilojoules per mole. Now here's the electronic structure of the halogens in the elemental form, and here's the electronic structure of halogens in the molecular form. Remember, halogens exist as diatomic molecules by mutual sharing of electron pair between the atoms involved in bond formation. Now as you go down the group, you observe that the distance between the positively charged nuclear protons and the shared pair of bonding electrons decreases. Sorry, it increases. So as you go down the group, the distance between the positively charged nuclear protons and the shared pair of bonding electrons, it increases. So not only that, the internuclear distance also increases. So as an outcome of this, the bond holding both the halogen atoms kind of weakens, or the strength of the bond decreases. So the bond energy or the bond strength decreases going down the group because of the increase in distance between the positively charged nuclear protons and the negatively charged shared pair of bonding electrons. So the positively charged nuclear protons, it kind of loses the attractive force or electrostatic force of attraction towards the shared pair of negatively charged electrons. And that is a major governing factor that leads to weakening of the bond strength. So here's a table depicting the bond energy in kilojoules per mole. So going by the theoretical concept, the bond energy should decrease. But here in the table, we see a exceptional behavior by fluorine molecule. So the bond energy in case of fluorine, it is less as compared to chlorine and bromine. So it is contrary to our theoretical consideration or theoretical concept. The reason behind this, now theoretically speaking, the bond energy in case of fluorine should be more, but the experimental outcome is that it shows a bond energy value of 158, which is lesser than that of chlorine and bromine. The reason behind this is because of repulsion. Repulsion between the lone pair of electrons in the outermost shell. Now there are two types of valence electrons. The first type is that which participates in the bond formation, which you call it as the bonding pair, and the rest of the electrons in the outermost shell is referred to as the non-bonding electrons or the lone pairs. So there are two types of valence electrons. One is the bonding pair, other is the lone pair. So bonding pair is the one that participates in the covalent bond formation between halogen atoms, and lone pair are those that do not participate in the bond formation. So due to the smallest size of the fluorine atom, the lone pairs, they come in close proximity, and that leads to repulsion between the electrons. So you may ask me, what about the other halogen atoms? They do have the lone pairs, but what about the repulsion in case of other halogens? There is repulsion even in case of other halogens like chlorine, bromine and iodine, but because of their increasing size, the repulsion gradually diminishes. And this repulsion between the lone pairs gradually diminishes going down the group. And the repulsion is least in case of iodine atom. Now halogens, as I already mentioned, they tend to form covalent bonds with non-metals like carbon and hydrogen. So hydrogen has one electron in its outermost shell, while fluorine atom has total of 7 valence electrons. Now hydrogen atom needs one more electron to complete its shell, that is duplet, while fluorine needs one electron to complete the octet. So both the atoms, they equally share this electron pair, and thereby a covalent bond is formed. So a covalent bond is formed between halogens and other non-metals by mutual sharing of electrons. So hydrogen reaction with fluorine to form hydrogen fluoride, hydrogen reacts with chlorine to form hydrogen chloride, hydrogen reacts with bromine to form hydrogen bromide, and hydrogen reacts with hydrogen to form hydrogen iodide. So after the reaction, both the atoms are happy with their completely filled outermost shell, and that is the driving force behind the covalent bond formation. So other examples that can be mentioned are that of halogenated hydrocarbons like methyl chloride, dichloromethane, chloroform and carbon tetra. Halogens also tend to form ionic bonds with metals to form salts. So halogens form ionic bonds with metals. For example, sodium reacts with chlorine to form the common salt sodium chloride, which is a solid, and iron reacts with chlorine to form ferric chloride. Here is the electronic structure of the halogens, the elemental form. So fluorine, it reacts with the metallic potassium. So when you observe the outermost valence shell of fluorine and potassium, you find that in case of fluorine, it needs one more electron to complete its octet, while potassium, it has only one electron in its outermost shell. So during reaction between fluorine and potassium, the potassium, it tends to lose the electron from its outermost shell to the fluorine atom, and thereby it attains the stable electronic configuration of argon. So potassium reacts with fluorine to form potassium fluoride, and after the reaction, potassium ion attains the stable electronic configuration of argon, while the fluoride ion attains the stable electronic configuration of neon. So this is the driving force behind the ionic bond formation between fluorine and potassium. And the same mechanism holds good even for the other halogens that reacts with potassium. So chlorine reacts with potassium. Potassium loses its outermost valence electron to chlorine, and ionic bond is formed. Potassium ion attains the stable electron configuration of argon, while the chloride ion attains the stable electron configuration of argon. So both the ions are happy with their outermost shell completely filled with electrons. And similar mechanism in case of reaction between bromine and potassium. Potassium loses its outermost valence electron to bromine. Potassium ion attains the stable electronic configuration of argon, while bromide ion attains the stable electronic configuration of krypton. And in case of the formation of potassium iodide ion by reaction between potassium and iodine, the iodide ion attains the stable electronic configuration of xenon gas. Now, detailed mechanism for the formation of ionic bonds between halogens and metals is dealt in detail in my previous tutoring session, and you can refer to that video where I have explained the driving force for the formation of ions and salts. Now moving on to the oxidizing power of halogens. Now the oxidizing power of halogen decreases going down the group, and halogens, by taking up an extra electron, they complete the octet and they kind of attain the stable electronic configuration of the nearest noble gas in the periodic table. So if an element like halogen takes one or more electrons from another reactant, then it is acting as an oxidizing agent. So oxidizing power decreases from fluorine to iodine for the reasons which I have already explained. So the transformation of halogen molecule with an oxidation state of 0 to halide ion with an oxidation state of -1 can be explained and understood by the reaction between the molecular chlorine and the bromide ion in the solution form. So chlorine, molecular chlorine converts the bromide ion into bromine. The bromide ions in the process lose electrons and the chlorine atom gains electrons. That is, the chlorine oxidizes the bromide ion and the bromide ion reduces the chlorine. So when halogen reacts, each atom gains an electron to give a halide ion. So oxidation state of chlorine atom is 0 in molecular chlorine, while the oxidation state of the chlorine atom is -1 in the chloride ion. So let us try and understand this particular redox reaction between chlorine and bromide ion with the help of electronic structures. So chlorine oxidizes bromide ion in the solution. So each chlorine atom in the molecular chlorine, it takes electron from the bromide ion, and thereby the molecular chlorine is getting reduced to chloride ion. And that is how bromine is released or liberated during the redox reaction between molecular chlorine and bromide ion. Now moving to the most important question relating to the halogens with reference to their oxidizing power, that is why fluorine can take only the -1 oxidation state while the oxidation state of other halogens range from -1 to +7. Let's find out. On examining the electronic configurations of the halogen atoms, we find that fluorine has no neighboring d orbitals to promote additional electrons. So therefore it can take only the -1 oxidation state. So when you closely examine the electronic structures or electronic configurations of the halogen atoms, you find that in case of fluorine, it has no neighboring d orbitals to promote an additional electron. So additional electron that fluorine atom is taking, it can be taken up by the half vacant p orbital. And there are no d orbitals, no neighboring d orbitals to take further more electrons or additional electrons. Therefore, fluorine can take only the -1 oxidation state. And what about the rest of the halogens? Now the other halogens like chlorine, bromine and iodine, they have access to the unoccupied d orbitals. So the other halogens can use their low-lying unoccupied d orbitals to enlarge or increase their octet. And that is how the other halogens like chlorine, bromine and iodine, their oxidation state ranges from -1 to +7 because of their d orbitals. Remember, now d orbitals can hold up to 10 electrons. So we very well know that s orbital holds up to 2 electrons, p holds up to 6 electrons, d holds up to 10 electrons, while f holds up to 14 electrons. So it is the ability of the d orbitals to hold up to 10 electrons gives the other halogens like chlorine, bromine and iodine to extend their oxidation state from -1 to +7. So it ranges from -1 to +7 depending on the reaction. So here's the shell diagram of fluorine atom where you find 2 electrons in the first shell and total of 7 electrons in the second shell. So first energy level, you find 2 electrons in the s orbital. In the second energy level, that is the L shell, you find total of 7 electrons, 2 electrons in the s orbital and 5 electrons in the p orbital. So here's the electronic distribution: 1s2, 2s2, 2px2, 2py2 and 2pz1. Now the 2pz orbital is half filled. It needs one more electron, and this will be the driving force for the fluorine to act as a powerful oxidizing agent. And talking about the energy level diagram, so low lying orbitals are filled first, or the low energy orbitals. So 1s2, 2s2 and 2p5. Here is the distribution of electrons, the respective orbitals. Now talking a little bit more about the ionic bond formation between the metals like lithium, sodium, potassium belongs to the group 1 of the periodic table, and halogens that belong to group 7 like fluorine, chlorine, bromine and iodine. So group 1 elements, they have 1 electron in their outermost shell. So hydrogen has 1 electron, lithium has 1 electron, sodium has 1 electron and potassium has 1 electron in the outermost shell. So elements of group 1, they behave similarly because they have the same number of valence electrons. They have only 1 electron in the outermost shell. And what about the halogens? And halogens, they have a total of 7 valence electrons in their outermost shell. And they need just 1 electron to complete the octet. So this is the driving force for the reaction between metals and non-metals. So here, halogens will accept an electron from the metals and thereby they complete the outermost shell. They complete the octet, attaining the stable electron configuration of the nearest noble gas. At the same time, the group 1 elements, they kind of lose the outermost electron and even they attain the stable electronic configuration of the nearest noble gas. Another outstanding feature, when you compare and contrast the group 1 and group 7 elements, since we are talking about reaction between group 1 and group 7 elements, when you compare and contrast these two groups, you find that the number of shells are one and the same. Now let us compare lithium with fluorine. Lithium has 2 shells, fluorine has 2 shells. What about sodium and chlorine? Sodium has 3 shells, chlorine has 3 shells. What about potassium and bromine? Potassium has 4 shells, bromine also has 4 shells. So going down the group, the number of shells increase, while going across the period in the periodic table, the number of shells remain the same. So hydrogen reacts with fluorine to form a covalent bond, while sodium reacts with chlorine by losing its outermost valence electron to chlorine, resulting in formation of ionic salt. So ionic bond is formed by a complete transfer of electrons from the outermost valence electron of the metal to the halogen. Now to summarize the discussion so far about the chemical properties of halogens. Now as you go down the group, the atomic radius of halogens increases. And what about the other parameters? The electron shells or the energy levels increases, effective nuclear charge decreases, electron shielding increases, ionization energy decreases, electronegativity decreases, reactivity and oxidizing power decreases, bond strength decreases, and halogens, they form covalent bonds with non-metals like carbon and hydrogen, and they form ionic bonds with metals to form salts. So you can refer my previous tutoring sessions for detailed explanation regarding the shielding effect, effective nuclear charge, and the trends in the periodic table. And these videos will provide you with a better understanding of this video content. So please do watch these videos first, and then you can again have a repeat watch of this particular